So now let's talk about the curse of the dimensionality. This is the problem that when we go to a larger set of dimensions, that certain types of algorithms, such as KNN, which is an instance-based algorithm, will suffer from performance, usually because the number of points that we need to have the distance metric mean something useful is going to be growing quite large. And usually we don't have a data set that can grow as large as we want. We have only a certain limited number of observations. Another big problem is that the distance between points becomes quite similar in high dimensions, making it hard to distinguish. And we're going to see what we mean by that. So let's illustrate the concept of the curse of dimensionality, starting with a single dimension, right? So here we have n equals 1, it's a line, and you might hear from various sources that you can have a fixed number of samples per dimension. So let's take that number to be 5. So for each dimension, we're going to have 5 samples. So here we have m equals 5. So that's just as we see here on the number line, or this line for a single dimension. What happens when we get to a higher dimensional space? So here we have a case of n equals 2. So this is the xy plane here. And to keep the same density of points, we're going to have to go to 5 to the power 2, right? So we have 25 samples. And that gets untenable pretty quickly because, for example, at n equals 3, we're already going to need 5 cubed or 125 examples. So as we go to a larger and larger dimensional space, we need exponentially more number of samples, right? And that's usually not the case that we can just acquire a large number of samples at an exponential rate. So this leads to the problem of data sparsity. We can't maintain the density of samples unless we're able to acquire so many more data points, keeping up with the exponential growth of the number of samples that you would need to maintain the data. So let's go to collaboratory. You're going to see this in your post 2 notebook. And just try this out on your own. So we've included some code for you to run and modify to check the curse of dimensionality. So it says here, recall the curse of dimensionality suggests that the larger the dimensional space that you have in the data set, the more difficult certain aspects of learning can become. And you can run this code. So I'm going to walk you through this just to give you a bit of a taste of what that means. So if you look at this code, basically there's a simple for loop. This is just going over the number of dimensions that we're going to use for the problem, right? So I can say 1 dimension just as we did there, 2, 3, 4, 10, 100, and 200. And then we're going to take a number of samples here, and we're just going to assume that we have a particular number of samples. You can try later on to run this line here, which suggests that you can grow the number of samples exponentially. It might get a little hairy. I suggest you don't do it past 10 because, of course, 2 to the 10 is already a million examples. It might already start to cause problems. Definitely don't try it for the very large digits of 200 or 100 there. And what we're going to do is we're going to generate samples from a uniform distribution between 0 and 1 for those 200 samples right now. And then we're going to draw a particular point, let's say a test point that we want to classify to, just like in KNN here, and say this is our target sample. Okay, and we'll generate some statistical information about what we're generating, how many dimensions and points, just so that you have some printout to see what's going on. And we're going to just calculate the distance between the points, right? Between the test point, which is xi, and all of the different points that we've calculated in our random sample. That's all of our xj over those 200 things. And we're just going to append all of those distances to an array and then find some particular statistical information, so the mean and the standard deviation over here. Okay? So you can see this from the collab notebook yourself. I've just taken a screenshot here. And the important thing is that you can see that the distances are growing, but not too quickly, even though we're ramping up the number of dimensions here. Between 4 dimensions to 10 dimensions, we get about a doubling of distance from 2.8 to 4.2. But even when we get to 100, you get 14, and 200, you get about 20. But that's not the key problem. The key problem is over here, okay, in the standard deviation. So you can see that the standard deviation of the distance between these 2 points grows rather slowly. Even when we get to 200 dimensions and 100 dimensions, they're not very distinct from each other. This indicates that there's a big problem, right? That when we go to a high dimensional space, the standard deviation of the difference between the points is not becoming large. And so all of the points are fairly far away from each other. They're not very discriminatively distinguished, even though these are completely random samples that we take. So let's summarize up what we mean by the problems of high dimensions as the curse of dimensionality. First and foremost, let's not forget that humans only work in a certain type of visual space, right? We have a few dimensional world, and it becomes really hard for us to visualize large dimensional space. We can probably have some understanding of up to 6 dimensions, but when we get to 10, 20, or even 100 dimensions, that becomes well nigh impossible. So most of us will compress this by using some type of dimensionality reduction algorithm. We'll cover something like PCA in the unsupervised learning lecture later in the semester. And as we've just illustrated, it's difficult to get a sufficient number of samples to maintain a good uniform density of the samples that would help us make the distance metric meaningful. Even when we do that, let's say we take a random sample, as we saw on the last slide, which you can play around with in the Python notebook, it becomes not very meaningful because most points end up pretty far away from each other. And the Euclidean distance metric that we might use as a first runner doesn't seem to be very meaningful. And this is just because in high dimensions, the hypercube is almost all edge space. Things are pretty far away from the middle. You can verify that by tweaking the code that we've seen. And, because a particular dimension, 2 points might be close, and all the other dimensions, they might be far away, it becomes that the distances are pretty uniformly distributed, and the standard deviation between points is pretty low. So what we want to say from this is it's really important, actually, in the long run, when you use k-means, if you're going to use it efficiently, to choose or design an appropriate distance metric to make sure that you're actually reflecting a useful measure of the similarity between points.